Recording in
So I'm just showing you the iterations one, but you can do the same thing for the iteration two, iteration three. So if you want to do the iteration two, and then on the left-hand side, and then that is all the components from the X2 with the subscript, the superscript 2. And then all the things from the right-hand side should be from the X with the superscript 1. So let's just collect all the components together, and then which means that this is our output for the iterations one, and that's the 3, 5, and then 25, 11, 1, and then -1, 1, 10, and then 15, 8. And I need to point out that you need to be very careful about the index here. The subscript here is the location, the index for the component. So this is the first component in the vector. This is the second component for the vector. This is the third component in the vector. This is the fourth component in the vector. And then the superscript here, we use the parentheses here to indicate the superscript here. And then this is superscript represent, this is the results after the kth iteration. And so this is 1, right? And then this is the results after the first iteration. And this is the X1 vector. So we collect all the component here, and then this should be the results after the first iterations. Questions?
Can you go back up to the like generally solved for XI?
The general, okay.
Sigma, or like the sigma notation for, yeah, that right.
Any other questions? This is our first examples, but for your homework or exams, I will ask you to perform the first iteration or second iterations, but in the computers, it will perform a lot of numerous iterations until the results satisfy that that criterion. And so I'm going to scroll down. So I just mentioned that the tolerance number is here, is the delta equals to the 10-3. And you would continue the iterations here in the computer until you have something satisfy the xk, subtract the previous iterations result, and then xk here in the denominator. And then if this is smaller than the tolerance results, and then we stop the iteration and then output that current iterations result there. And this is how the Jacobi's methods work. And then we have the concrete numerical examples on the lecture notes, but you can take a look at lecture notes I posted on the Canvas, and I'm not going to show you here in the class because I cannot do the copy and paste today. I'm using the new iPad. I haven't set it up yet. And so you can take a look at the lecture notes. Let's see, there's something else I want to mention about the Jacobi's methods. And this is the updating rule, right? And then we just solve for the equation, and then solve for the x1, x2, x3, x4. And then for the right-hand side, we replace all the things here, the variables, replace all the things here with the previous steps things. And then this is the current step things. And this is the updating rules. And then let's take a look if we have a general matrix, and then how can we get that updating rules. And so also I want to mention that in the Python code, it's faster to do a matrix operations than the for loop. And then I have included the reasons at the end of this lecture notes, because it has a better efficiency algorithm. It has better memory layout, and then it can have parallelizations in the computation. So in the Python, it's better to use matrix computations than the explicit for loops there. So now I'm going to introduce the matrix format for this method because it's more efficient to compute such iterations here with the matrix formulations in the Python code. So now let's take a look at the matrix formulation. And let's see. So the updating rules, actually we want to calculate such an updating rules for the Jacobi mappers, And the T is the n by n matrix. And then the C is the vector n by 1 vector. And we want to know the T and the C for this Jacobi mapper. And then if we know the T and C, and then we know the updating rules for the Jacobi mappers. And this is the matrix format for the Jacobi's mappers. So let's see how can we divide such a such matrix in the Jacobi's mappers. So first, let's recall what we have here. We are going to solve for AX equals to B, and then the important component here is just the A. So let's just split the A into the several components here. That is the D matrix, L matrix, and the U matrix. And then for the D, it represents the diagonal matrix. And then L is the lower left, and then U is the upper right. So let's see. So diagonals of the A matrix, it looks like this. It's A11, A22, and then to the A and N. And then all the things up beside out of this diagonal are 0. And then what is the lower left? Lower left matrix, it should be, so lower left matrix of the A, and then which means that we only take the lower left part from the A, and then all the things are 0. So here on the diagonal are 0, and then above the diagonal are zeros, and below it is just the A21, A31, and the AN1. And here we have A32 and all the way to the A, this is the A22. Okay, A21, A22, and the A31, A32. Yes, it's correct. And then here is just the AN2. And here is just the AN in row and the N minus 1. And this is the lower left matrix. And then what about the upper right? And then that is the symmetric things about the diagonal. And we have the zeros on the diagonal, and then 0 below the diagonals. And then above the diagonal, we have the A12, A13, and then A1N, and then all the way to the AN minus 1. And we have all the non-zero elements, not non-zero elements, we have all the elements here above the diagonal. And that is, we split the matrix A into the diagonal, and then the things below the diagonal and the things above the diagonals. And this is how we split the matrix. And now, don't forget our original goal here. We want to derive this matrix, the T matrix and C matrix. And now let's take a look at the magic here. The magic here is we want to solve such an equation, right? And then now with the splitting here, we split it into the 3 matrix, which means that we have the D plus L plus U matrix, and then times the X equals to B. And let's move the things around. And then I'm going to just keep the dx on the right hand side, and then I'm going to move the L and U to the left hand right hand side, and then plus B. And if you take a look at here, why I keep the D here, because it's easy to do the inverse for the D, because this is a diagonal matrix. The inverse of the diagonal matrix is just the so here, if you want to take the inverse of the D, and then it's just A11 inverse, A22 inverse, and then or 1 over A11 or 1 over A22, 1 over AN in the diagonal matrix. And it's easier to take the inverse here for the diagonal matrix. So and if the D inverse exists, and then if it exists, it's just a 1 over A11, 1 over A22, and so on and so forth. If this inverse exists, and then we can take the inverse for the both sides. We have the D inverse here, and then D inverse for the right hand side, and then we have the X value. It's just the D inverse L plus U and the X, and then plus the D inverse B. And as you can see here, this is the same steps we have here. We have above. We are solving for the X, and then from the equations AX equals to B here, we are solving for X. But here you cannot stop here because we don't know X at the very beginning. So you cannot use a solution to solve for solutions. And so now we are going to put the K minus 1 here, and then this is a K here. And then which means that we are going to we use these equations to be our, so here we are going to put the K here, and then put the K minus 1 here, and then this is D inverse B. And so this is our general updating rules for the Jacobi's methods. And you can just form the matrix based on the A matrix. And then you can just tell the Python, okay, this is my updating rules. And this is my matrix T, and then this is my matrix, my vector C. And then use such matrix and vector to update with the Python code's matrix computations. And so we call this, usually we just say this is the matrix TJ. I'm just using the subscript here to know that, to say this is the Jacobi methods. And then this is vector C, and then I am going to use this subscript here, CJ, to say this is the vectors for the Jacobi methods. With such notations here, we can write the iterations method as the TJ xk minus 1 and then plus the CJ. And this is the general Jacobi method. Does that make sense? Any questions here? Any questions here? So instead of that, instead of updating in this way for the for loop, because if you want to implement this solution updating rules here in the Python code, and then you are going to use the for loop. But below here, you can use some matrix multiplications in your Python code, and this would be more efficient. And let's see how to calculate the TJ and the CJ for the one concrete examples. And I'm going to give you one example here. Example. So let's see. Actually, I'm going to use the same example here. We have the same system of equation. This is a new iPad. I don't know how to copy and paste to. Okay. This is the equations we have just now. And so let's see what does the A matrix looks like. The A matrix looks like this. It's just the 10, -1, and then 2, 0. And we just ignore the right hand side because here we are just calculating the DLU matrix. And then this is -1, 11, -1, and then 3, and 2, -2, 10, and -1, and then 0, 3, -1, and then 8. So from this matrix, we know that, okay, for the diagonals, and then we just have the 10, 11, and then 10, 8. And what does the L matrix looks like? The L matrix is the things below the 0, 0, 0, 0, 0, 0, 0, 0, 0. And this is the lower left matrix L. And we have the -1. We just take all the things out from the lower left part below the diagonal. And then we have the -1, 2, -2, and then 0, 3, -1. And what about the upper right triangular part? We have 0, 0, 0, 0 on the diagonal, and then -1, 2, 0, -1, and then 3, and then -1 here. And all the things below it is just zeros. And so this is the diagonal matrix. This one is the diagonal matrix. This one is a D, and this one is the L, and this one is the U. You can denote your matrix in this way. And after that, you can just tell us that, okay, the T, do you remember what the T looks like? The TJ, that is the Jacobi matrix, updating matrix in the Jacobi methods. And then it is just the -D times negative D inverse times the L plus U. And that is the -D inverse and then plus L plus U. And it's just the D inverse, right? The inverse is just the 1/10, 1/11, 1/10, and then 1/8. And times the L plus U, and then times the L plus U, and then it's just the 0, 0, 0, 0, all the things here, and then -1, 2, -2, 0, 3, -1, and then I'm going to do the sum for the L and U, and then -1, and then 2, 0, -1, 3, -1, and you can do the multiplications here. And the first one is just the first row, and then times this one. And then first row times the second one is the second column is the first. So here, first row, first column, and then we got the 0. And then for the first row times the second column, and then we got this one. And then that is the -1/10. So you are going to do all the multiplication here, and then you will get such results. And then this is the matrix. And then 0. I'm going to copy them all the result here, but you can see the multiplications, the matrix multiplications here is super easy because the D inverse is just the diagonal matrix. And zero here, and then 3/8 and 1/8, and then the 0. And this is a TJ matrix. This is the updating matrix in the Jacobi methods. We also need to calculate the CJ. And CJ is the updating vectors in the updating rules, the vectors in the updating rules in the Jacobi methods. So let's see, what does the Jacobi vectors, this vectors looks like? It is just a D inverse B. So we have D inverse B. And what is the B? The B here is the 6, 25, and then 11. The right hand side here, 6, 25, 11, and 15. And that is just the 6, 11, and 25, 11, negative 11, and then 15. And then we times this one with the D inverse here. And you would get the result, and then that is the 3, 5, and then 25, 11, and negative 1, 10, and then 15, 8. The last one is 15 over 8. So this is how we compute the things. We substitute all the things into the D inverse and B, and then you do the calculation. But the very important things in this example is to figure out your D and your L matrix, your U matrix, and that's it. Oh, I forgot the negative sign, right? Yeah. Let me see. I forgot the negative side. Yeah. You're right. I forgot the negative side here in front of the very first one. So this one, it should be the 1 over 10. And then this one, it should be just the, yeah, this is the correct result, 1 over negative 5. Yeah, I forgot the negative sign here. So we need to be very careful. And so if you want to calculate the TJ matrix and CJ matrix in your homework, you need to memorize this formula and then figure out the DLU, and that's it. Any questions? And on your lecture notes, it actually gives you some numerical results to see how to use this matrix to update the xk from the xk minus 1. So now let's go to the another method, and then this another method is an updated version for this method. It's a better one, but it's just with a small change from the Jacobi's method. So let's go back to the Jacobi's method here, and then to take a look at the calculation here. So let's take a look at this example, right? And then you're going to use the x0 to update the x11, and then you get the x11. And here it has some values related to the first component, right? But after the first round calculation, you already get an updated value for the x1 component. So let's see. Let's see. This is the Jacobi's method, right? Jacobi's method. And you know this. x1 k minus 1 and the x2 k minus 1 and to the xn k minus 1. And actually you are calculating in this way. You are making use all the element here and then calculate first, and then you have the x1k, and then after the first step, and then you calculate the second step. But here you are making the same set of the information, and then here you are going to make use of all the information from the lab here to calculate the x2k, right? But the good information is that, the good news is that actually we can use the updated information to update the x2k instead of using the old data. So now you already update the x1k from this data set, right? And then let's say, okay, at this time we are going to, okay, now after this round of the calculation, after this first step, I'm going to replace this information with the xk. And that is the updated value. And then we are going to use this updated value, and then all the things here below is from the K1 minus K1 minus steps, and then to update the x2k. And then after you get the x2k, and then replace the x2k minus 1 with the x2k, and then we get updated values here. and then use the left-hand side information to update the X3K. And this is the upgraded methods, and then we upgrade this version, and then to this one we call is the Gaussian pseudo methods. A pseudo method, it should be SIE, and this is the idea for the Gaussian pseudo methods. So instead of using the same set of the information, the old set of the information, so for each step here, once we get the X1K, and then we replace the X1K minus 1 with the X1K to update our X2K. And then once we get the X2K, and then we replace the X2K minus 1 information here to update all the things here below, one by one, and then we replace the K minus 1 information with the new one, the new data. Does that make sense? Any questions here? Does that make sense? Someone looks confused. Someone looks confused. Let me express this one. So here, this is the Jacobi's method, right? And then this is the information we use here, X2K minus 1. And we are using all these informations to update the same things. So we are updating the X1K, and then we are also using this set of data to update the X2K, right? And then we use all these information to update the X2K, the third component to the nth component. But in the Gaussian pseudo method, we just change one thing. So in the Gaussian pseudo method, we are updating the values on the right-hand side, and then in the same time, we replace something in the data set. So this is our data set, right? This is the data set we use to update the next iterations result, this current iterations result. And then in the meantime, we are updating these values on the right-hand side. We are also changing some things in the data set. So let's say from the first iterations, X1K minus 1 and the X2K minus 1, Xnk minus 1. And then from the first iterations, and then from the first step, we use this set of the informations to update the first component. And then we got the X1K, right? But now we stop a moment, and then we are not going to update the second component here. Instead of updating the second component, we are changing the data set here with the updated value. So I'm going to change this value to the updated value. So this is, it will become the X1K. So now if we want to update the X2K, and then now I'm going to use this updated value and the old data set here to update the X2K. And once you get the X2K, and then now we are not going to go to the X3K directly. We are going to do one more step to replace these things with the X2K. And then this is the old data set, right? And we are going to update this value and then to the X2K. And then we use this data set to update our X3K. Does that make sense? So we are going to use some updated information from the data set along the process. And this is the Gaussian pseudo method, and it could have a fast convergence results. And actually, let's take a look. Let's take a look at here, and we are going to write out the general formula here. So the general formula. So let's see the updating rule here, xik. Let me just copy down the things we have in the Jacobi's methods first, because this is the upgraded versions of the Jacobi's method, right? So let's see what we have in the Jacobi's methods. We have the sigma sum j equals to 1, and then to the n, and then j doesn't equals to I, right? And this is the Gaussian's, this is the Jacobi's methods. And then all the informations are from the k minus 1, right? And this is, and then plus the bi. And this is the Jacobi method. But now, if you take a look at this process, the x2k is using, so let's say this is x3k, and the x3k is using before the 3 component, and then we are going to use the updated message, and then from the 3, the third component to the n component, we are going to use the old data, right? So now we are going to use some new data before the index I. So we are going to change something here. Before the index I, we are going to use the updated message. So before the index I, so I'm going to sum up from the j equals 1 to I minus 1, and I'm going to use the new data, xjk. And before, up to the index I, I'm going to still keeping, I've still used the old data here. I still use the old data, j equals to 0, I plus 1, and then to the n. Aij and then xj, and then because this is old data, and then the superscript here should be k minus 1. And this is the Gaussian's pseudo rule. Gauss pseudo rule. Pseudo mapper. Misspelling. It should be pseudo. Sorry. Pseudo. Gauss pseudo's methods. And let's see one concrete example for this. And then we just using this formula to update the values on the left-hand side for the k iterations. And let's see, this is the same method, same examples as we have here. And we are going to solve this linear equation. But now we are going to use the Gaussian pseudo methods instead. Copy and paste here. This is an example, and then let's see. Let me just copy them everything from the Jacobi's method because it's just an upgraded version of the Jacobi methods, and then we just need to change some things in between, and then that's the updated version, right? And so let's just copy them everything, and then let's see what we need to change. So for examples, we have screw up a bit more, right? This one. This is the Gaussian's pseudo methods. And it's also on the lecture notes I posted on the canvas. And let's see. But in the concrete examples, it would be very easy to do it. You don't need to memorize this. You need to be familiar with how to operate the values in the right hand side and the left hand side. So let's see. This is the Jacobi methods. And I'm also copying them everything from the Jacobi methods below. And then let's see what we need to change. And I'm going to copy them, the Jacobi's methods. Okay. Jacobi's methods. And this is something from the Jacobi methods, and then we just need to change some things a little bit to upgrade these versions to the Gaussian's Gauss-Seidel methods. And so as we have here in the Gaussian-Seidel methods, and then we know that from before the index I, and then we are going to use the updated message. And then after the index I, we should use the old data set, right? And so let's take a look at here in the Gaussian, this is Jacobi's method, right? And then before the index 1, and then we are going to use the updated message, but there's nothing before the index 1, right? And then after the index 1, we are going to use the old data set. And let's see, for the component 2, and then the index 2, and then before the index 2, we are going to use the updated message. So what is before the index 2? It's 1, right? So for the x1, this is old data, but for the x1, we are going to use the updated message informations for the Gaussian-Seidel methods. So here we are going to use the x1k. And after the index 2, we are keeping the old information. So this is k minus 1. And let's take a look at the x3. So for the index 3, what is in front of it is the index 2 and then index 1. In front of the things in front of the index 3, and then we are going to use the updated information. So we need to use the k superscript here, which means that we are going to use the updated information here for the x1 and then the x2. And after the index 3, we are going to keep the older old informations. So let's see, for the index 4, what is in front of the index 4? It's the x2 and the x3, x1, but we don't have the x1 on the right hand side, so we don't need to change anything. And then, but for the x2 and the x3, we are going to use the updated information. And that is the information from the k. Information from the k step. And this is the updating rule for the Gaussian-Seidel methods for this example. And let's take a look at one concrete example here. So if the initial guess is 0, 0, 0, 0. And then let's take a look if we go for one iteration and then to get the x1, and then what is the x1 looks like. And let's see. So for the x1, I'm going to substitute all the 0 here, and then to the first equation, and then I got the 3 over 5, and then this is just the first component. And then what about the second component? The second component here, you need to be careful. We cannot substitute all the 0 to the second equation because here we have updated value for the x1. So this one should be the 1 over 11 times 3 over 5. 3 over 5, and then plus, okay, for the x3 and the x4 is from the zeros, the initial data here. So this is the x0. So here we plug in 0, 0, and we got 0, and then plus the 25 over 11. And the result is approximately this, is approximately 2.3272. And then this is the x2 one. And for the x3 one, and that is, we are calculating the third component for the x1 vector. And here we are substituting. So for the x1 here, x2 here, we are using the data. This is the updating data. x1 and then x2, and then substitute it to here. And then for the x4, we're still using the previous steps information, which means that this is the x4 0. And then this is the 0 here. And if you use this data, and then you would get, so which means that we have negative 105, and then times the updated value for the x1, and then plus the 1010, and then the updated values is around this one. And plus the old data for the x4, and then it's just 0. And then subtract the 1/10, and this is something from the third equations. And at the end, you will get an approximation value for this one, the decimals approximations value. And this is how we update for the x3 for the first the x1 vector. And then for the x4 component, and then x4, this is the fourth component for the x1 vector. And now for this one, you will see we are going to use the updated data for the second component, third component, and all the components, x1, x2, x3. And although we don't have the x1 here. So we are going to use the updated vector, updated data here on the right-hand side. And we got -3/a, and then updated data in the second component should be the 2.3272, and then plus the 1/a, and then the updated data for the the third component should be the -9873, and then plus the 15/a. This is the constant in the fourth equation. And then approximately we have the if cell is 0.8789. And you can combine all the components together, and then to get the x1 vector. And then the x1 vector is just looks like this: 0.00, 0.6000, and then 2323, 0.9871, 0.87189, and then take the transpose, because we expect that for the vector here, it should be the column vector. And does it make sense, the updating procedures for the Gaussian Seidel methods? You just need to understand all these calculations examples for your homework and your final exams, but you can also take a look at the code I posted on the Canvas to see the actual implementations on the Canvas. There's a code posted on the Canvas as well. So as we did before, we have the matrix format, right? I mentioned that it's very efficient to use the matrix computations in the Python. So I'm going to derive the matrix formulations for the Gaussian Seidel method as well. So let's see the Gaussian Seidel method. The Gauss Seidel method matrix formulation. And let's write it in this way. So we are going to rewrite them, the AX equals to B in the following way. And so for the first one, the first equations, and then we know this one is the X1 is from the current step information, is the new updated one. And then on the right-hand side is just the old data from the previous step. And then minus 1n, xn, k minus 1, and then plus the b1. And for the second equation, we knew more things about the variables, right? And then for the second equations, we have a21, x1, and then also we got the new updated informations about the second component, And so we have the updated information for the second component here. And on the right-hand side, we got negative A23X3. And then this on the right-hand side, this is the index after the 2. And then on the right-hand side, that's the information from the previous steps, the K minus 1. So and so forth, subtract the A2n, xn, K minus 1, and then plus the B2. And you will see this happens at the end. We have all the updated information on the left-hand side for the first component to the n component. And then we have x1k, and then an to x2k, and then to all the way to an and x and k. And then on the right-hand side, it's just the bn. So this is the Gaussian Seidel method. It looks like, and then on the left-hand side is the updated information for each steps. And then for the first step, we have the updated information for the first component. And then for the second step, and then we have the updated information for the first two components. And then for the n step, we have all the updated information for n component. And it looks like this, right? So we are going to still use the L matrix, U matrix, and diagonal matrix to represent these Gaussian Seidel methods. So on the left-hand side, you will see this is just the lower left matrix with the diagonal part. And so we have on the left-hand side, we have L plus D, and then multiplied by the K vector. So let's see K iterations result, and this represents the left-hand side part above. And then what about the right-hand side part? The right-hand side part you will see is from the A12, A13, A1n, and this is A23, right? And they are the upper right triangular part, and then but with the minus sign. So we have on the right hand side we have minus u, and then on the right hand side all the information is from the old data, so it should be the xk minus 1 and plus the b vector. And now let's solve for the xk, and then we just get the inverse. Get the inverse on the both sides, and then we get the xk, and then it equals to the L plus D inverse, and then times the U xk minus 1, and then plus the L plus D inverse, and then B. And as we did before, we give it notations for the matrix here. And then these notations, this one is the iterations matrix in the Gaussian Seidel method. And then so we have the T matrix, and then because this is Gaussian Seidel, and then we use this subscript here, G, to represent this is the matrix in the Gaussian methods. And for this one, I'm going to denote it as C, and then with the subscript G to represent this is Gaussian Seidel method. So you can write it with this shortcut, xk equals to the tg and the xk minus 1 and plus cg. You can see the iterations method here. We have a general form here, just the T matrix times the xk minus 1, and then plus a vector c. And then for different methods, you have different T matrix, different C vectors. This is the things I mentioned here, and you need to memorize this formula, and then the TG matrix formulation, and then the CG matrix formulations, and also you need to memorize the similar things for the Jacobi's methods. And that's all the things for today. And if you have more questions, and then you can ask me after the class, or you can just go to my office hours in the afternoon as well. Any question, you can also come here. Yeah. Any question? Any questions?